So we resume our lectures again after the mid-sem exam and the mid-sem break. So far we have learned about different techniques to evaluate average orders of functions which are additive. So this was the Turan-Cubilius inequality. Then we also looked at a technique called Perron's formula, which teaches us how to evaluate average order or estimate it in terms of analytic properties of the Dirichlet series f of n over n to the s, and this technique works very well for suitable classes of arithmetic functions, not necessarily additive or multiplicative. The idea is that you should be able to analytically extend the Dirichlet series into a function which is of a nice form. So far, and we used the latter technique to also derive the prime number theorem. So this is essentially what we have done so far. Now, we are going to learn some very beautiful techniques to estimate average orders of functions which are multiplicative and which take values in the unit disk. That is, your absolute f of n is less than or equal to 1. So these could be complex valued functions, but they lie inside the unit circle. Okay, so before we start understanding how to evaluate or how to estimate average orders of these type of functions, let us give some motivation for both these functions, for both these topics 1 and 2. We had suitable motivation coming from probability, and likewise for the third topic also there is a very nice probabilistic motivation. So for this we have to review quickly the notion of characteristic functions of random variables. So here is the situation. We've got a probability space omega, a sigma algebra on omega, and a probability measure. So this is a and x, let x be a random variable on the space, and let us take real valued random variables. Now, corresponding to a random variable, we have the notion of distribution functions. So, f sub x of x, for any x in R, for any little x in R, f sub f of x is the probability so this probability is the same as the probability here. So probability of capital X less than or equal to x, we all know that this is called the distribution function of x. All right. So we want to study the existence of the distribution of x and relate it to average orders of certain nice functions. So, this takes us to the notion of the characteristic function of a random variable. So, what is this characteristic function? It is defined as the characteristic function of a random variable x in the probability space as given above is defined as the expected value of e raised to the it of the random variable x. So, if capital X is a random variable e to the itx, where for any t, okay, so this characteristic function is denoted as phi of t, not to be confused with the Euler-Phi function. So, phi of t is denoted as the expected value of e raised to the itx. So, what is the importance of the characteristic function of a random variable? Before we come to that, let me just also define another notion, namely that of weak convergence. So, suppose you have a sequence x2 of random variables not necessarily on the same probability space. So, if you have a sequence this is said to converge weakly to a random variable x, which could also be on another probability space, if the following happens. If the limit f sub x sub n of x as n goes to infinity is equal to capital F of x, that is the probability that capital X is less than or equal to x, for every x in R where f is continuous. Okay? And let us take real valued random variables. So, if this happens, then we say that our sequence x n's converges to capital X. Alternatively, we may also say that the distribution, corresponding distribution functions converge weakly to the distribution function of the random variable capital X. Okay, so alternatively, we have, so we define f sub n to be equal to the distribution function of capital X sub random variable capital X sub n. This, we say that this converges weakly to f. There are different types of notions of convergence of random variables. We will be focusing on weak convergence. Now, like I said, these random variables don't necessarily have to be defined on the same probability space, and as before, a very natural example comes from probability spaces defined with respect to finite subspaces on sets of natural numbers. So, let us take in the context of the kind of functions that we have been looking at. So, for arithmetic functions, f which take real values, what we do is we consider the probability spaces omega sub n on, okay. So, the set of all subsets of omega sub n, and on each such space we have the probability measure mu sub n, where as before our omega sub n is just the set 1, 2 up till n, okay, and your nu sub n is defined as follows: for any singleton I, it just takes the uniform probability 1 over n, and so our arithmetic function can be viewed as, so f sub n is just f restricted to omega sub n, and so this is how we learned to view arithmetic functions as random variables. This was a brief review in case you forgot, since we are meeting after a long time. So, with this in place, what does weak convergence refer to? So, we say that, so we have, so what does weak convergence here mean? Okay. So, we have limit as n goes to infinity, okay, of this distribution function here, which is, what do you have? We have this is just the number of natural numbers up to capital N, for which f of n is less than or equal to x. Okay. The question is whether this converges to some function, some capital F of x for all x lying in the set of points at which your function f is continuous. Okay. If this happens, then we say that there is a weak convergence of these random variables to capital F. Another short form of saying this is, if the above happens for some capital F, suitable capital F, then we say that F has a limit law. Okay. And now what we do is we recall a very important theorem from probability, which I am just going to state without proof, which relates the notion of weak convergence to the characteristic functions of our random variables that we are looking at. So, this is an important theorem, and this gives us the motivation for looking at multiplicative functions whose values lie inside the unit circle, inside or on the unit circle. So, let us take, as before, a sequence of random variables, not necessarily on the same probability space, and let us take phi sub x sub n be their characteristic functions. Okay. This theorem, which is, it tells us that, so this is called Levi's continuity theorem. Okay, so I think the correct pronunciation is Levi's. I will confirm before the next class. So suppose you have this. So let f sub n denote their distribution functions. Then our distribution functions corresponding to these random variables f sub n okay. So the statement of the theorem is that this sequence converges weakly to some function f if the following happens, if and only if the characteristic functions corresponding f sub n converges to a function phi which is continuous at the point 0. Okay. So, to say that a sequence of distribution functions f sub n converges weakly to a distribution function f is equivalent to saying that their corresponding characteristic functions converge to a function, to some function which is continuous at the point 0. So, in order to study weak convergence, we can translate the study into the convergence of our characteristic functions. So, this is where the motivation comes from. And now, if this happens, okay, so if you have your characteristic functions converging to some suitable function which is continuous at the point 0, then in this case, this function phi is significant in the sense that it turns out to be the characteristic function of capital F. Okay. So, to say that Fn converges to F is equivalent to saying that phi Fn converges to phi F, and your phi sub f sub n. Okay. So, if you have that phi sub f sub n is converging to phi which is continuous at 0, then this convergence is in fact uniform in any compact subset of R. So, this convergence of phi sub f sub n to phi sub f is uniformly convergent. This convergence is uniform on any compact subset of R. All right. Now, in the context of the arithmetic functions, we are looking at, if we wanted to apply our continuity theorem to that, context, then what we have to study is the characteristic function. So, you have some function f. Okay, so what you need to do is you need to study the expected value of e raised to the I t f of n, right? And notice, so if f is additive, it implies that the function g of n, which you define as e raised to the I t f of n, where t is any real number, okay, this function will turn out to be multiplicative. And if your function f is taking values on the real line, then clearly absolute is exactly equal to 1, right? So, that is why we want to study functions which are multiplicative, average orders. So, expected values are average orders. So, we want to study the average orders of functions which are multiplicative and whose values lie in this context exactly on the unit circle. But we generalize this a little bit and address those functions which are multiplicative, but which take values not only on the unit circle, but also inside the unit circle. So, this leads to a set of very beautiful theorems, and we are going to initiate the study today. So, the first theorem in this context is Delang's theorem, which states the following. Let us have a function which is multiplicative with values lying on the unit disk. Then, furthermore, we had seen before that when you have multiplicative functions, they can be, with the help of the notion of Euler product, they can be studied in terms of their values at primes and prime powers, and continuing in that direction, it would be enough for us to prove a theorem or prove a condition for G with respect to its values at prime numbers. So, if the following happens, if the sum 1 minus the real part of G of P over P, okay, as the sum runs over all the primes, if this is finite, then the average order of our function g of n is equal to the following product. The product runs over all the primes up to x, and you have for each such p, you consider 1 minus 1 over p into summation mu going from 0 to infinity g of p raised to the nu So if you have this, then as x goes to infinity. Now, why would you even guess something of this form? The proof will make it clear. Okay, so here's what we do if you want to prove this theorem. Let us first sketch the main points of the proof. So what we do is, instead of looking at g of n, we consider certain like nicer forms of g. So this is what we do. So for each, let us take, so step 1. So I'm first going to tell you briefly what are the main steps. So the first step, for each y, okay, any y, let us take any y and let's fix that. Let us consider the multiplicative function coming from g of n in the following way. We denote this as g sub y of n. Such that, how do we define? To define a multiplicative function, it is enough to define it at its prime powers. So g sub y of p raised to the nu, any prime power, is equal to g at p raised to the nu, provided your prime is bounded above by y, okay, and it is 1 if p greater than y. So this behaves in some form, this is, you can think of it as some kind of a descent of y, of g, where now it is taking exactly the same values as g at those prime powers where the primes are less than or equal to y. I am not saying that the prime powers are up to y. Prime powers could be very, very big, but that prime p itself has to be less than or equal to y. Okay, now if so, you can define this function g sub y of n as follows. Once you know how it behaves at prime powers, you know how it behaves at all the natural numbers n. And of course, you also know that g sub y of 1 has to be equal to 1. So given this, what we do is, we are able to show that the mean value of g sub y of p raised to nu is very similar to the mean value that you want to take here. Okay. So we show that summation n up to x of g sub y of n, okay, it turns out to be equal to x times a function m of g sub y, which I am going to define shortly, plus little o of 1 as x goes to infinity, where what is m of g sub y is defined as the function. You have the same product, but with the products, with the primes running up to y instead of x. Okay, so suppose you have 1 minus 1 over p into summation nu going from 0 to infinity g of p raised to the nu over p raised to the. Okay. So what we show is that the essentially what this is saying, this equality here, okay, is saying that as this function m of g sub y is the average order of your function g sub y, and that is why we denote it as m of g sub y, m referring to the word mean, okay. So, the mean value of g sub y is this function. Then what we show is that our g sub y's are actually good approximations to g, and therefore, what happens as y goes to infinity is that you end up getting the corresponding equality for your big function, the universal function g, okay. So, next step what we show is the following. So, this looks a little strange, but let me explain. So, what we do is we take, so we write, suppose you have a function which is a complex valued function, and you also know that it is taking values on or inside the unit circle, then we write this as absolute of g of n raised to the e raised to the I times what you call the argument of g of n, where you choose your argument. Okay, this is just the corresponding angle. What I mean to say is that, so this lies between 0 and 2 pi. Okay. All right. So, with this in place, now what we do is we define an additive function let us call it theta of n as follows. This theta of n, again, to define an additive function, it is sufficient for us to define it at prime powers. So, for any prime power p raised to the nu, theta of p raised to the nu is defined as our angle corresponding to g of p raised to the nu, okay, where your okay, if you have g of p raised to the nu not equal to 0, then the corresponding angle is your theta, and if g takes the value 0 at a prime power p to the nu, then you just take this to be equal to 0, all right. So, suppose you have a function which you define at prime powers in this way, you can then consider a more general additive function coming from the corresponding function defined at the prime powers, okay. So, with this what we do is, exploiting the fact that your theta is an additive function and applying the Turan-Kubilius inequality in a very nice way, which we will discuss in the next lecture and just sketch for now, what we end up showing is the following. Let us set capital A of x to be equal to summation of theta of p over p. Okay. So, then it turns out that our m, the mean value of g sub y times e raised to the minus I times capital A of y, it converges to a finite limit let's say sum A as okay, not to confuse with the, let's call this limit B, okay, as y goes to infinity. Okay, this is really the step where most of the work happens. And finally, we make the observation that if I take e raised to the minus I times a of x, okay, times 1 over x into summation of g of n, this converges to m, the mean value, the m of g sub x as defined before for y equal to x, times e raised to the minus I a of x plus little o of 1. Okay, so using the fact that these elements converge to some finite limit as y goes to infinity, we are able to derive that the average order or the mean value of g of n multiplied by e to the minus I a of x is the suitably constructed function, gives you something nice, and from this you can deduce immediately that your 1 by x, that is which is the quantity that you are after, okay, this converges to m of g sub x, which is exactly what you were looking for, as x goes to infinity. And this proves the theorem. Okay. So, to prove this theorem now, we first look at, so what do we have? We have this universal function g, which takes the values that make it a multiplicative function, values lying in the unit disk. Okay. So, what we do is, corresponding to these, we consider, like, let's call these local variants of your function g sub y's, and we prove this corresponding mean value theorem for g sub y's first. Now, this is a very elementary argument, and in fact a very nice application of the Mobius inversion formula. So, let's work this out. Details. So, step 1. Let us do the following. Let us define h sub y as follows. Okay. Let h sub y be denoted as the convolution of the Mobius function and g sub y. Therefore, what is this? This is the sum as d runs over all the divisors of n, mu of n over d times g sub y of d. Okay. So, in particular, this will immediately tell you that if g sub y is multiplicative, so is the convolution h sub y, and what you also know, the values at prime powers and h sub y of p raised to the nu, it turns out to be equal to your difference of g sub y p raised to the nu minus g sub y of p raised to the nu minus 1 if nu is greater than or equal to 1 and p is less than or equal to y. Okay. Whereas, if p is greater than y, this will just turn out to be equal to 0. Right? Now, what is the significance of this? Now, since h sub y is the convolution of mu and g sub y, what does it mean? By Mobius inversion, we also have that our g sub y of n can in fact be written as summation over h sub y of all those d's, where d run over positive divisors of n. This is just following from our definition of h sub y and the Mobius inversion formula. So, with this, why is that helpful? By writing g sub y of n in this form, we find a nice simplification for the average order of g that we are looking for. So, it turns out that summation n less than or equal to x g sub y of n, okay, this is a kind of calculation that we've done several times in this course. So, you have an inner sum running over, and therefore, you interchange this, and by interchanging it, what you end up getting is, first you run over all the numbers up to x, okay, h sub y of d, and in the inner sum you have all those n's up to x which are multiples of d. In other words, you simply get the greatest integer of x over d. This is a routine calculation which we have performed many times in this course, and therefore, you can write this as x over d plus an error term of the form O of 1. So, you write this as x times summation d up to x h sub y of d over d plus O of summation d up to x absolute h sub y of d. All right. Now, what we do is, we write this as, we first consider all the numbers from all the positive numbers. So, d going from 1 to infinity h sub y of d over d, okay. Then from this we have to remove those numbers d which are greater than x. So, we have, what we do is, we write this as plus O of another function h sub y of x, where what is h sub y of x? It is, first of all, those numbers running up to x absolute h sub y of d, okay, minus, I take x times d greater than x of h sub y of d over d, okay. And in fact, since we need this to be O, we basically need an error estimate of h sub y of x. What we can do is that we can actually take this to be the sum, okay, and actually we have absolute h sub y of d's here. So, what do we do next? We have to estimate what our h sub y of x is, and of course, we also have this term. Let us first just focus on this main term here, okay. Let us take our sum. So, look at d going from 1 to infinity h sub y of d over d. Now, this is a multiplicative function. H sub y of d over d is a multiplicative function. So, we can write this in terms of an Euler product provided suitable convergence conditions hold. Now, suppose, imagine that we do not have to worry about convergence conditions. What happens? Okay, so, you have to write this as product of p up to y, and what do you have? H sub y. So, nu going from 0 to infinity h of p raised to the nu h sub y of p raised to the nu over p raised to the nu. Now, you see the right hand side converges absolutely. Okay, you can show that. So, each of these sums converges absolutely, because beyond a certain so each of these converges absolutely, since these are bounded above by some absolute constants, and therefore their products, you have products over a finite set of primes. Okay, so the product also converges absolutely, therefore the corresponding sum also converges absolutely, and therefore this Euler product is valid in this case. So, if you want to study this sum, you just study the corresponding Euler product, which is what we do, and we also, so what do we do here? We write this as product of all the primes up to y. Okay, so for nu equal to 0, you just have 1, okay, plus nu going from 1 to infinity, but you already told me that your h sub y of p raised to the nu can be written as this. So, g sub y of p raised to the nu minus g sub y of p raised to the nu minus 1 over p raised to the nu. Okay, these are also convergent, absolutely convergent sums, and by a simple rearrangement exercise, you can actually just write this as 1 minus 1 over p times summation nu going from 0 to infinity g of p raised to the nu over p raised to the nu. Okay, which is your m of g sub y, exactly what you were looking for. And now you have, all you have to do now is look at the error term. Okay, so this will give us, once we estimate the error term, let's do it in the next class, it will tell us the mean value of these localized function g sub y's, and then we go from these local functions g sub y to the universal function g. Okay, so that is where your Turan-Kubilius inequality plays a very nice role. So this is what we will cover in the next lecture, and we stop for today.